Hello everyone, I'm Jiao coming from Syracuse University. I'm here to present our work, the design and implementation of a capacity-variant storage system. This is a joint work between Syracuse University and Dankook University. At a high level, the capacity-variant storage system is designed to mitigate the aging-introduced performance degradation on modern SSDs. So to start off, let's first investigate the impact of aging on modern SSDs. The figure here shows the real throughput of a real enterprise-grade SSD under its different edge states. We edge the device through randomized by writing about 100 TB of the data each day. And during the morning hours, when the server is free, we measure its read-only I/O performance, so the performance changes are not caused by garbage collection or other factors, but from aging and wear. So, as shown in the figure, the performance of the SSD decreases as it wears out, and by the end, writing a total of 9 petabytes of the data decreases the throughput by 38% for the sequential reads and 37% for the random reads. In this work, we note that such aging-introduced performance degradation is worsened by the existing storage system abstraction, which fundamentally limits the benefits of the SSD. Specifically, with the current storage system abstraction, the logical capacity of a storage device is determined and fixed during the manufacturing. It assumes that the physical capacity of a storage device doesn't change over time. This abstraction is built around the traditional HDDs and expects the device to exhibit the file stop behavior. However, it is not accurate for the SSDs. The physical capacity of an SSD naturally reduces over time, and the number of bad blocks increases as it ages. During this process, the flash memory blocks fail partially and exhibit more errors. So as a result, the existing fixed capacity abstraction requires the SSD to implement the well-leveling algorithm and over-provision their physical capacity in order to maintain an illusion of a fixed capacity device. This in turn complicates the error handling mechanism within the device and manifests into the fail slow symptoms. Moreover, when the original exported logical capacity cannot be maintained, when too many blocks become bad, the entire storage device becomes unusable. Even worse, SSD manufacturers nowadays typically adopt denser flash memory chips in order to decrease the overall cost and increase the device capacity. The rapid increase in flash memory density has come at the cost of reduced reliability. The figure on the right shows the reported error rates in recent publications, and this trend indicates that the flash memory errors are already a common case. So I will outline the design principles of the proposed capacity-variant storage system in the next few slides. To address the performance degradation and high error rates caused by aging, we proposed a capacity-variant storage system. In the traditional system, the devices treat the performance and the reliability for a fixed logical capacity. On the other hand, in the capacity-variant storage system, the logical capacity of an SSD is not fixed. Instead, it gracefully reduces the exported logical capacity as it ages by mapping out edge blocks which would exhibit the error-prone behavior, and thus enables a better trade-off between capacity, performance, and reliability. We enable capacity variance by designing kernel-level, device-level, and user-level components. The first component is a capacity-variant file system which dynamically tunes the exported logical capacity based on the edge states of the underlying storage device. The device-level component, the capacity-variant SSD, maintains its performance and reliability by mapping out edge blocks earlier. The user-level component, the CV manager, provides necessary interfaces to the host and orchestrates the capacity-variant file system and the SSD. When CVSS maps out flash memory blocks and its physical capacity decreases, the CV manager will get notified and provides a recommended logical capacity to the capacity vendor file system and automatically managing the capacity of the entire system. Due to the time limit, I will focus on our file system level design and the device level components. Please refer to our paper for the more information. So to support capacity variance, the file system is supposed to export an elastic logical capacity to the host. Since log-structured file systems are demonstrated to perform well on modern flash storage devices, CVSS uses F2FS as a baseline file system, and the data layout is shown here. The meta area contains the checkpoint, block bitmap, the file index, and the reverse table. The data area contains 3 data logs and 3 node logs. So there are 3 requirements for supporting the elastic logical capacity. First, user data must be carefully maintained in order to avoid data loss. Any valid data within the to-be-shrunk area must be relocated before reducing the capacity. Second, the logical capacity adjustment should be finished in an online fine-grained manner, and the time it takes should be minimal with a low overhead. So the question now is, what are some potential approaches to achieving elastic logical capacity, and what are their trade-offs? Since our design is based on a log-structured file system, there are 3 potential ways to achieving the elastic logical capacity. And one option is to use a non-contiguous address space. With this approach, the file system can internally decouple the address space exported to the user from the LBA. When the logical capacity should be reduced, the file system identifies a range of free space and restricts the user from using it, for example, by marking that as allocated. With this approach, the logical capacity adjustment can be efficiently achieved with the low overhead, with the lowest upfront cost, as the primary task involved is to allocate the readily available free space. However, this approach increases the file system cleaning overhead and fragments the entire address space. Second, similar to the segment cleaning or defragmentation, the file system can physically relocate the valid data from the to-be-shrunk area to a lower area region before the capacity reduction process. This approach maintains the contiguity of the entire address space. However, data relocation exerts additional write pressure on the SSD, and the overhead is proportional to the amount of valid data copied. Moreover, user requests are potentially stored during the reduction process. Lastly, the data can be relocated logically at the file system level instead of at the SSD level by taking advantage of the already existing SSD internal mapping table. This approach requires the introduction of a new SSD command to associate data with new LBAs. However, it effectively mitigates the address space fragmentation issue and incurs negligible system overhead, as there is no physical data rewriting. To integrate the remap approach into the capacity variant file system, we revised the interface proposed by PriWorks and tailored it for capacity variance. Our modified command enables the file system to safely shrink the logical capacity with low overhead by remapping data from their old LPNs to new LPNs without the need for actual data rewriting. We extend the current NVMe interface to include remap as a vendor-unique command. For example, when the capacity variant file system wants to remap the LPN5 data to the LPN3, the corresponding remap command will be issued. Upon receiving the remap command, the device will check the mapping table and find the data is stored in the physical page 6. It will then check the out-of-boundary area of the physical page 6 to validate its state. The mapping entry of the logical page 3 will be updated to the physical page 6. And lastly, the mapping entry of the physical page 6 will also be updated as well. So next, I will outline the design decisions of the capacity-variant SSD. The goal of a capacity-variant SSD is to maintain consistent performance even when aged, allow user-defined performance, and achieve a better trade-off between capacity, performance, and reliability. To achieve that, we first modify its block management scheme. Conventional SSDs consider blocks as either good or bad, and such coarse-grained management fails to meet different performance requirements. Instead, in the capacity-variant SSD, we define 3 types of the flash memory blocks: young blocks, middle-aged blocks, and the retired blocks. Young blocks have a low error rate, and the middle-aged blocks have a higher error rate while still meeting the performance requirements from the host. Retired blocks are worn-out blocks and edge blocks which will be excluded from storing user data. This scheme enables the CV-SSD to map out edge blocks earlier based on the user requirements, effectively treating capacity for the performance and reliability. Since the goal of a capacity-variant SSD is to keep most in-user blocks at peak performance, a capacity-variant SSD implements wear focusing to concentrate the wear on a small amount of flash memory blocks, and such edge blocks can be mapped out later. As a result, a capacity-variant SSD doesn't implement wear leveling algorithm, as it degrades all of the blocks over time. Wear leveling is an artifact designed to ensure that most, if not all, flash memory blocks are wearing out at roughly the same rate, which opposes our goal of allowing partial failure. Moreover, a recent large-scale study on millions of SSDs reveals that wear leveling techniques in modern SSDs present limited effectiveness and can introduce high system overhead. The figure here illustrates different behaviors of a wear leveling algorithm. Depending on the workloads or system configurations, a wear leveling can be too moderate, too aggressive, or even incorrect. Such counterproductive operations can be avoided by foregoing the wear leveling and adopting capacity variance. However, simply avoiding using the wear leveling is insufficient to achieving wear focusing, as there are 2 processes affecting the life cycle of a flash memory block: the block allocation and the garbage collection. Since retired blocks are not used in CV-SSDs, there are 4 scenarios when considering data characteristics. As listed here, the type 1 and type 4 scenarios are ideal cases, as they help to coverage the wear among blocks without affecting the performance. However, for the type 2 cases, when write-intensive data are written to young blocks, it levels the wear among blocks. For the type 3, when read-intensive data are written to middle-edge blocks, it will incur high error correction overhead within the device. To address that, we first modify the block allocation policy of the capacity-variant SSD. Specifically, CV-SSD will prioritize young blocks for the garbage collection rights and the middle-edge blocks for the host rights. With that, the write-intensive data will be inevitably rewritten to a middle-edge blocks by the host. To address the cases where read-intensive data are written to middle-edge blocks, we modify the garbage collection policy to consider invalid ratio, edging status, and data characteristics. By doing so, the read-intensive data stored in the middle-edge blocks will be relocated to young blocks during the garbage collection process. I will show some of our evaluation results next. The capacity-variant storage system is implemented upon the Linux kernel version 5.15. CVFS uses F2FS as a baseline file system due to its virtue of being a log-structured file system. The CVSSD is built on top of the FMU, and the table here outlines its major configurations. We use synthetic and real workloads to evaluate capacitive random storage system and compare it with 3 different techniques: the traditional storage system, AutoStream, and the TT-Flash. Specifically, AutoStream uses multi-stream interface to automatically assign a stream ID to the data according to their access pattern, and the SSD can place them accordingly later. For the TT-Flash, it reduces the time latencies of an SSD by utilizing the data redundancy scheme to reconstruct the data fast. We designed the evaluation with the following 3 questions. First, can the CVSS maintain performance while the underlying storage devices ages? Second, how does CVSS perform compared to other techniques on the real workloads at the overall application level? Lastly, can CVSS extend device lifetime given different performance requirements? So let's first investigate the performance benefits of CVSS under synthetic workloads. The figure here shows the measured real throughput of a traditional storage system and a capacitive random storage system under their different edge states in terms of the terabytes written. So as the figure shows, in the capacitive random storage system, the performance is maintained by treating capacity. Overall, CVSS outperforms the traditional system by up to 0.7 times with the same amount of hosted writes. In the CVSSs, the degraded mode will be triggered when its physical capacity decreases to a level where it will be insufficient to maintain the current user data. In this case, CVSS will update its internal policies to slow down further capacity loss. As shown in the figure, after the degraded mode, the future capacity loss is slowed down, but the performance is compromised. The figure on the right shows the measured average write throughput over the experiment. For the traditional storage system, when the wear leveling is triggered, the write throughput drops significantly. On the other hand, for the capacitive random storage system, it provides a stable and higher write throughput without the wear leveling. We next evaluate capacitive random storage system at the overall application level using a set of k-value traces from the Twitter production. The figure here compares the average KIOPS over the experiment across the entire device lifetime. As the figure shows, overall, CVSS outperforms the traditional storage system by 1.42 times on average and by up to 3 times under the Trace38 workloads. On the other hand, for the TT-Flash and AutoStream, they present limited effectiveness in mitigating the fast slow symptoms. We further investigate how CVSS extends device lifetime given different performance requirements. Since TT-Flash introduces additional write pressure coming from its internal data redundancy, it is not included in this experiment. So from the figures across the workloads, CVSS accommodates more hosted writes and significantly extend the device lifetime given different performance requirements. We also observe that for the traditional system, CVSS outlasts it by a small margin without the performance requirements, but by a large margin when a high performance is required, which indicates that for the traditional system, most time the device experiences a low performance. For the AutoStream, it achieves a longer device lifetime than the traditional storage system, except for the no performance requirement case, which indicates that it incurs higher data relocation overhead coming from wear leveling towards the end. There are more results included in the paper. If you are interested, please refer. To summarize, in this work, we proposed a capacitive random storage system. CVSS relaxes the fixed capacity of the storage devices and thus enables a better trade-off between capacity, performance, and reliability. CVSS consists of 3 different components: the CVFS, CV-SSD, and the CV manager. We also observe that a similar idea has been commercialized in the phone products developed by the Xiaomi Inc. For the future work, we plan to add the read support to the existing system, and we expect the new optimizations and features will be continuously added to the existing system. Thank you very much for your time, and I'm happy to take questions.